Okay. Hello. I've been told that I can start, so I'm going to go ahead and do that. So I'm John. I'm the CTO of Verdice. Originally, this talk was supposed to be given by our CEO, Yufeng, but unfortunately, he wasn't able to make it. And so with a few days' notice, I had to take over. And so this is going to be fun, because I definitely know all the slides. Okay. So let's go ahead and start talking about account abstraction. So I'm sure a lot of you have been hearing a lot about account abstraction lately, and so I'm just going to spend a little bit of time in the beginning to give a brief overview of how it works. And so if we look at like an EOA right now, you have an individual and they've got a key, and that key is going to give them access to several things. So it's going to give them access to things like their current ETH balance, their nonce, and so on. However, other than that, there's a lot of things that an EOA doesn't get. And so that's where smart contracts come in. So with a smart contract, you get a lot more things. So you get all of the things that you do with an EOA, but you get access to some additional aspects. So you get access to code, and you also get access to storage, which is great because that means that now you can do more things than you could with an EOA. And that's why smart contracts have more utility than just end users. So the reason why account abstraction has become a thing is because EOAs have several issues, right? So you end up having a key that is deeply coupled to an individual, and so if you lose that key, then you've lost tokens. There are other issues that we can talk about, but I will do that a little bit later. And so here is that later. So basically, another issue is you can only pay for gas and stuff like that with ETH, whereas a lot of people would like to be able to pay with other tokens. But in order to pay with other tokens, they often have to do manual swapping and stuff like that, and possibly incur fees that they weren't otherwise expecting. They can also only use a single type of curve in order to sign a particular transaction, and so people who want different security models or perhaps greater security now have to use or are forced to use this particular ECDSA scheme. And then finally, there are other questions like, what if you want someone else to pay your gas? Right now, you have to pay gas. There is not a very good way for other people to pay it for most end users. And so that's where the EIP 4337 came in. And so for those of you who don't know, that is the standard that defines what we call account abstraction. And so the important part is here what you can see is account abstraction ends up defining a lot of different things. It defines user operations, entry points, and so on. And I'll get to what all of these mean later. You don't have to read all of that. The important aspect here is it has concrete roles for people to actually perform, and it has descriptions of what someone should be doing in order to fulfill that role. So the reason why that's important is because these entities and their interactions can be encoded into logic and then checked. And so that's exactly what we're going to do. We're going to take a look at the specification, encode the behaviors that we see as logical formulas, and then use formal verification in order to ensure that people are actually following the specification correctly. And so just to give you a little bit of more of an overview of how this works, essentially, where this starts is you have a user. Previously, a user would submit a transaction, and when they submit that transaction, they would do it directly with the blockchain. Here, they're going to take an operation called a user op, and they're going to hand it to someone called a bundler. That bundler is then going to be responsible for submitting all of the transactions, all of the bundled transactions, to an entry point. That entry point is then going to be responsible for one, paying the bundler, but two, it's also going to be delegating the user operations to the appropriate source. So this could be like a payment master. The paymaster is going to be the one who pays the bundler fees for things like gas. It could be sending the operation to a factory to create new contracts, or sending the operation to a wallet, and that wallet will be doing a number of operations like transferring funds to another user. So if we look at some features of account abstraction, it allows you to do things like pay for transactions in currencies other than ETH. So that's great, because now, rather than having to worry about how much ETH you're going to be spending and having to make sure you transfer or swap the appropriate amount of USDT or something like that to ETH, you can just go ahead and spend your USDT. It also allows you to ask other people to pay for gas. That can also be really good if you're, like, let's say, performing a service for someone, or if someone is asking you for payment. And finally, it allows you to support different validation schemes. So you're not now stuck to a single ECDSA curve. You can now use a different scheme like multi-party signatures and stuff like that. So, and then finally, there's support for additional recovery schemes. But these are all of the good features of account abstraction, but there are things that can go wrong. And so we took a look at publicly available GitHub repositories, and specifically issues that people had posted in these repositories. And we're using that in order to determine some of these violations that I talked about previously. So I'm going to show you a couple of these violations that were fixed by the developers of these repositories, and also describe how they could have been found rather than manually by someone inspecting the code using formal verification. So in this case, what happened was, you can see down in that red part down at the bottom, there was a line that was removed and replaced with the line to the right. The reason why that happens is because in the specification it says that the max fee per gas is going to be the minimum amount of fees that someone can accumulate. However, the function that max fees per gas replaced performed a minimum between max fees per gas and another value, which meant that technically someone could have been charged gas under the minimum that they specified, which is against the particular EIP specification, because there are reasons why you might want to pay higher gas in order to ensure that your transaction is being picked up correctly. Another reason, or another bug that we ended up seeing in here is one right here. So this one is implied by the EIP specification, but it's not exactly well defined. So in the EIP, it states that the stake value is expected to be above the min stake value. However, a lot of things can be above the min stake value, and when people are performing operations like casting or ensuring that values fit into a particular int, you can have overflows. And so an important thing to note is that the EIP specification has a lot of specs that perform or that provide safety properties, but that doesn't mean that it is comprehensive. There are other things that need to be checked. So for example, for values such as this one, it's important to ensure that people are properly maintaining or properly checking the values of, or the values that can be taken by individual variables. And so finally, this one here is also missing from the specification. Basically, what you can see on the left is, it's performing an operation that should be guarded by a check of the user signature. So essentially, it's checking to see whether someone should be paid. However, previously in the code, there was no check to make sure the user was who they said they were. They weren't validating that the signature was correct. And so there are several locations where the signature needs to be validated. Otherwise, someone could, let's say, submit a user operation, claim to be a potential user with a bogus signature, and if that's not actually validated, then, well, they can actually end up stealing funds that way. And so on the left-hand side is the original code. The right-hand side is where they added in this specification, or this code that ends up checking that the signature actually matches the one that, or the signature for the operation is correct. Okay, and so now let's take a look at how we might be able to formally verify some of these properties that are both implicit in the EIP standard and explicit in the EIP standard. So the way that we're going to do that is we first need to encode these specifications into some logical formula. And so the way that we do that here is we can either just encode it as some sort of mathematical formula over the values of the contracts. So that's what's done in the first case. Or what we can do is we can define certain predicates that will help us actually define relationships in the contract itself. So that's what's done down below. So if you're curious, the one down below basically states that there's a data dependency between the user operation and the public key, and then that in turn is control dependent on the return value. So it basically states that somewhere someone has to actually check the return or check the public key in order to properly return with some value. And so basically the specification used here will use linear arithmetic formulas as well as some custom predicates in order to allow people to encode these properties. Then what we're going to do is our tool is going to take in the source code as well as the property that's going to be checked, and it's going to use a technique called abstract interpretation. So the important thing about abstract interpretation is it is going to reason very abstractly about the program, but it needs to know how to do that. And so that's where this abstract domain comes in. I'm not going to go into depth about how abstract interpretation works, but if you're curious, catch me after. And so after taking in those things, it's going to reason about the source code itself, and then it's going to report any potential violations of those specifications or common vulnerabilities. So now let's take a look at the work that we've done so far. So far we've developed a total of 71 specifications from the EIP standard. We've collected 24 benchmarks that are buggy from open source account abstraction wallets. And this is going to include some popular account abstraction implementations, such as Ethereum's reference implementation in Sol Wallet. And finally, each benchmark is, so each benchmark is going to correspond to a specification violation. And so that's why the number of benchmarks that we have doesn't correspond to the number of specifications that we have, because we are specifically looking here to see how we might be able to find violations. And so each benchmark, we're looking to make sure it returns a counterexample. So now if we take a look at the specifications, most of them, 56 I believe, are explicit in the EIP standard. However, 15 of them we identified are implicit specifications, like the public key specification I showed earlier. In addition, we found specifications over a number of the different entities that I showed you earlier. And so some of them apply to user operations, most of them apply to the wallet itself, but basically it defines the behavior of all aspects of the account abstraction. So if we look at some of the preliminary results, because this is ongoing work that we're doing, currently we have evaluated 24 of those benchmarks, and we have found that actually all but 2, which would be 22, are solvable. And if you're curious about the size of the benchmarks, that's shown on the right, but essentially each one of the contracts, I think, has an average number of lines of code around 350. And so the important thing here is this can actually be used to identify bugs, and in most cases, it does. So just to give you a little bit of a takeaways, the EIP standard does specify safety properties, but it does not completely specify the necessary safety properties that one should check for. So in addition, issues in these implementations can also be found by looking for specific specification violations from the EIP standard. And basically, it's possible to check your code by using logical reasoning like this formal verification method. So in conclusion, there are a couple of other talks that Verdice will be giving over the next couple of days. So in, I think, a couple of hours, there's going to be a talk about Magi, which is a formal verification infrastructure for Cairo. And then tomorrow, there's going to be a talk about Picus, which will automatically find under-constrained bugs in ZK circuits. In addition, we partner with a lot of people in this space. We're a security company. Notably, we are one of MetaMask's preferred auditors for their snaps. And those are our socials if you want to learn more. Thank you.